This is the 33rd video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. In this video, we're going to discuss the general principles of assembly language. We have thus far constructed a CPU that can handle two types of instructions: register-type instructions that take two registers as input, and immediate-type instructions that take one register and an immediate value. As we saw in videos 29 through 31, a program is just a sequence of instructions. To run a program, we need only load RAM with the instructions we want to run. The challenge is, of course, how we can write, or perhaps more importantly, maintain these long strings of ones and zeros. Today, of course, we use high-level programming languages like C and Java. But back in the time of the very first computers, the solution was to use assembly language. At a high level, an assembly language is just a human-readable version of a machine language. For example, instead of typing this, we'd type add T1, T2, T3. Likewise, instead of typing this, we'd type add I, T1, T2, 6. You can see here how each component of these assembly instructions corresponds to a field of the machine instruction. Once you've written some assembly code, a program called the assembler converts the human-readable statements into the corresponding ones and zeros of machine code. Now, based on what I've said thus far, it may seem like assembly serves the same purpose as other high-level programming languages. However, there's one important difference. Each line of assembly is intended to correspond to exactly one line of machine code. In high-level languages, each line of code often corresponds to several machine instructions. This is because the purpose of high-level languages is to help you express yourself as naturally as possible. Today, the goal of most new programming languages is to reduce the amount of translation you have to do between the idea that's in your head and what you have to type to make the computer do what you want. In contrast, the goal of assembly language is to minimize the amount of translation that needs to be done between what you type into the computer and the actual instructions that are executed on the hardware. In today's world, where computing power is cheap and human labor is expensive, we're almost always best served by high-level languages that make programming as quick and as bug-free as possible, even when the resulting program is not as fast as it would be had it been written in a more hardware-oriented language. However, in the 1940s and 1950s, when computers were new, computing power was expensive and limited. At the time, assembly languages provided just enough translation to make writing and maintaining code feasible. We simply didn't have the technology to do better, at least not in a cost-effective way. As computers got more powerful, programming languages slowly evolved from being primarily CPU-centric, where the code clearly reflected the CPU's approach to solving problems, to being primarily human-centric, where the code more clearly reflected the way we tend to, or want to, think about problems. Now, even up into the early 1990s, performance-critical code was often written in assembly because the compilers of the time could not optimize the code as well as a human expert. Today, however, compilers and interpreters have improved so much that writing code in assembly is rarely helpful. The compiled code is as fast, if not faster, than the hand-optimized code. And even when it is faster, computing power is so abundant and cheap that it's usually more cost-effective to buy a slightly faster CPU than to pay for an expert to make the code faster. We study assembly in this course because the goal of the course is to learn how CPUs work. Part of that process is learning what the high-level code you write looks like by the time it actually reaches the hardware. And it's of course much more practical to study this using assembly than using machine language. Oh, and you may have noticed an asterisk pop up a few minutes ago. At the time, I said the high-level idea is that each line of assembly corresponds to one line of machine code, which lets us see exactly, rather than conceptually, what the machine is doing. However, we'll soon see that this rule often gets stretched a little bit. Remember, the original purpose of assembly was not to teach computer organization, but to make programming easier. As a result, shortcuts have crept in over time that violate this one-to-one correspondence between assembly language statements and machine code. I'll point these out as they come up. Also, to be clear, there are many different assembly languages. Each type of CPU has its own assembly language. Or perhaps it's more accurate to say that each machine language has its own corresponding assembly language. In this class, we'll be learning the assembly for the MIPS CPU. Once you know MIPS assembly, it'll be fairly straightforward to learn other assemblies like ARM or SPARC or x86, even though these other assemblies contain some features that are very different from MIPS. In the next video, we introduce MIPS assembly and the Mars MIPS simulator.